Authur Compton. Authur Compton discovered that light can behave as a particle as well as a wave, and he coined the word photon to describe these newly identified particles of light. Compton's discovery was one of the most pivotal revelations that led physicists to conclude that objects once thought to be particles can behave like waves, and objects once thought to be waves can behave like particles. Later, with his graduate student Luis Alvarez, Compton showed that cosmic rays contain positively charged particles. During World War II, Compton played a crucial role in the development of the first atomic bombs. Authur Compton was born in the town of Worcester, Ohio, USA on September 10, 1892. His father, Elias Compton, was a philosophy lecturer and minister of the Presbyterian Church who became dean of the University of Worcester. His mother, Authur Asperger, was a college graduate and a former school teacher who served in the board of managers of children's homes. She was the Golden Rule Foundation's American Mother of the Year in 1939. Authur was the fourth child. His older sister Mary, whose school grades were higher than any of her brothers, became a missionary in India. His two older brothers, Kyle and Wilson, enjoyed illustrious careers, Kyle as a physicist and president of the Massachusetts Institute of Technology, and Wilson as a businessman and president of Washington State University. From age 14, Authur attended Worcester's preparatory school. His well-educated parents raised him in a house full of books, and he soon developed a keen interest in science, especially astronomy and powered flight. At age 12, Authur read an astronomy book and was hooked. His first telescope was not very powerful. He got a thrill when he realized that a puzzlingly shaped heavenly body he was looking at was Saturn. His telescope was not powerful enough to resolve Saturn's rings. At age 17, in 1910, Authur pointed his homemade camera at Halley's Comet and took a photograph of it. He treasured the photograph for the rest of his life. In 1907, age 15, Authur became interested in the Wright brothers' powered flights that had taken place in 1903 to 1905. He became so fascinated that he began designing and building model aircraft as large as himself from wooden frames covered with paper. By the time he was 16, working in a barn, he had built a full-size glider, a triplane whose width was 27 feet and length 12 feet. His building materials were pine wood, cloth, and piano wire. The total cost was less than $35, financed by doing chores for neighbors. He flew his glider successfully in spring of 1909, age 16, and learned a great deal about aviation. But his parents were so worried it would be killed flying it. He agreed to stop. He disposed of his glider in a huge bonfire. In 1909, he published 2 papers on aeronautics, one in Fly and one in Aeronautics. Scientific American published a letter he sent them about planes. Authur was torn between his love for science and his Christian faith, which was pulling him in the direction of becoming a missionary. His father, himself and a church minister, told his son he would probably perform a greater service to Christianity as a scientist than a missionary. Authur Compton enrolled for a Bachelor of Science degree at the University of Worcester then known as the College of Worcester, and majored in physics. He found himself drawn to experimental work rather than theory. In 1913, Compton left home for Princeton University, New Jersey, with the intention of doing graduate work in engineering. However, he spent his first year doing a master's degree in physics and decided to become a physicist. In 1914, he began working for a PhD in physics in Princeton. He graduated in 1916 with a thesis entitled "The Intensity of X-ray Reflection and the Distribution of the Electrons in Atoms." He then worked for a year as an instructor at the University of Minnesota and 2 years in engineering for Westinghouse. At Westinghouse, he recognized his true vocation was pure science rather than commercial research. In 1919, Compton won a prestigious scholarship that allowed him to travel overseas to do postdoctoral research at the University of Cambridge's famous Cavendish Laboratory. There he studied the scattering and absorption of gamma rays and became friends with the discoverer of the electron, J.J. Thomson, and the discoverer of the proton and atomic nucleus, Ernest Rutherford, both of whom he admired greatly. In 1920, aged 28, Compton returned to the USA to be head of physics at Washington University in St. Louis, Missouri. Compton was tasked with building the tiny department into a top-class entity. In fact, Compton did much more than this. He played a major role in answering a question whose inconsistent answer had plagued scientists for centuries. Is light a particle or a wave? Two brilliant 17th century scientists had taken opposing positions. Isaac Newton, who said light behaved like a particle, and Christian Huygens, who said light behaved like a wave. In the 19th century, the question seemed to have been settled. James Clerk Maxwell's famous equations established that light was a wave, and moreover indicated that visible light was a small part of a larger electromagnetic spectrum. Maxwell's work represented the zenith of classical physics. However, by the end of the 19th century, classical physics was in trouble. It could not, for example, predict the colors of light emitted by hot metals. To solve the hot metal color problem, Max Planck proposed that when hot objects emit light, the light's energy must always be a multiple of a certain number. With this proposal, Planck was able to bring physics theory back into agreement with the real-life observations. Today we call the number Planck introduced into physics the Planck's constant. Planck's idea changed physics forever. If light energy comes only in multiples of a certain number, then other values of energy are forbidden. This was the beginning of the 20th century quantum revolution that changed physics dramatically and permanently. In 1905, Albert Einstein explained something called the photoelectric effect, the fact that shining ultraviolet light on metal causes the metal to eject some of its electrons. Einstein said that effect could be explained if light behaved like a particle and if particles of light carried an amount of energy given by the light's frequency multiplied by Planck's constant. If you think about it, this seems weird. In the same breath, Einstein is saying light has a frequency, which means it's a wave, but he is also saying it behaves like a particle. Today we call this particle of light a photon. The word was actually coined by Authur Compton. Eventually, this is light wave or particle weirdness became an intrinsic part of quantum theory. In fact, light can be either. Its behavior depends on circumstances. Sometimes light's wave-like character takes center stage and its particle-like character bows out, while at other times the roles reverse. However, Einstein's 1905 proposal that light could behave like a particle was rejected by most scientists. Then, in 1923, Authur Compton published results showing that Einstein had been right all along. Compton was working with very high energy light in the form of X-rays, observing how X-rays interacted with electrons. He was not trying to show Einstein was right. His purpose was to investigate how electrons are distributed in atoms using particles similar to those used by Lawrence Bragg, who showed how the position of atoms in solids could be reduced using X-rays. In 1922, Compton observed that X-rays were modified by interacting with electrons. Following interactions, X-rays had lower frequencies and longer wavelengths, meaning they had lost energy. When he examined the paths and energies of X-rays that had interacted with electrons, the only interpretation that made sense was that the X-rays and electrons behave like two colliding particles, very approximately like two poles balls colliding. Compton established that a single X-ray does not interact with several electrons. A single X-ray interacts with a single electron. Thus, I was led to the now familiar hypothesis of an X-ray particle colliding with an electron and bouncing from it with reduced energy, the lost energy appearing as the recall energy of the electron. Authur Compton. After all, it is not easy to believe that scattered rays of any kind can differ in frequency and wavelength from the primary rays. If you whistle in front of a barn door, the echo you get back sounds just the same as the sound that goes out. That kind of reasoning sounds rather convincing, but when you find an experiment that the wavelength is actually changed, you can see that there must be something wrong with the wave theory. It may be fair in the United States a conviction of the fundamental validity of the quantum theory. Authur Compton. Compton published his work in the Physical Review in May 1923. In technical terms, he established that X-rays can behave as particles with momentum given by the equation first proposed by Einstein, where P is momentum, H is the Planck constant, V is the frequency of the light, and C is the speed of the light. In 1924, Luis de Broglie proposed that all matter have wave-like properties. In 1927, Clinton Davison and J.J. Thomson's son, George Paget Thomson, proved that electrons can behave like waves, and so wave-particles duality was born. Authur Compton was awarded the 1927 Nobel Prize in Physics for his discovery of the Compton effect. De Broglie was awarded the prize in 1929, and Clinton Davison and George Paget Thomson in 1937. Today, we know that in the quantum world of photons and electrons, whether something behaves as a wave or a particle depends on its environment. In 1912, Victor Hess carried out a series of experiments to investigate the source of mysterious radiation that had been detected by others such as Theodor Wolff and Domenico Panini. The results of his experiment caused Hess to conclude the results of my observation are best explained by the assumption that a radiation of very great penetrating power enters our atmosphere from above. Compton's first experimented with these cosmic rays in 1921 after Ernest Rutherford prompted him to think about the underlying reasons for radioactivity. Compton learned that Marie Curie had speculated that the radium's radioactivity was caused by its somehow capturing cosmic rays. Compton's experiment tested Curie's theory. Compton took a sample of radium to the bottom of the Grand Canyon, a place reached by fewer cosmic rays than places with higher elevations. The radium's radioactivity did not change at all, indicating that the radioactive elements were not made radioactive by cosmic rays. In the 1930s, scientists were still arguing about what cosmic rays actually were. There were two opposing schools of thought. One, cosmic rays are electrically charged particles. And two, cosmic rays are uncharged electromagnetic radiation like X-rays, but with much higher energy. From the University of Chicago, where he had been appointed to the professorship in 1923, Compton organized expeditions to various locations on Earth to observe cosmic rays. With his family, he traveled 40,000 miles, making observations as far apart as northern Canada and Australia and visiting Europe, India, and New Zealand. The teams discovered that the highest numbers of cosmic rays were observed at locations far from the Earth's magnetic equator. This proved that cosmic rays are largely made up of charged particles. In 1932, Compton's graduate student Luis Alvarez built an array of Geiger counters to study cosmic rays. In 1933, Alvarez and Compton published a paper in the Physical Review establishing that cosmic rays are positively charged particles. They made an error, however, in pointing to the positrons rather than protons as the positively charged particles they had detected. Compton gave much of the credit for the work of his younger graduate student. Nazi Germany's invasion of Poland in 1939 plunged many European countries into a state of war. In 1940, America had not yet entered the war, but talk of war was in the air. Compton, a devout Christian, disagreed with his church minister, who was arguing pacifism. Compton said, "As long as I am convinced, as I am, that there are values worth more to me than my own life, I cannot in sincerity argue that it is wrong to run the risk of death, or to inflict death if necessary in the defense of those values." Compton played a key role in the development of the first nuclear weapons. British scientists told their American colleagues they believed an atomic bomb could be built in about 3 years. Early in 1941, Compton was appointed to lead the team of American scientists investigating whether this was realistic. Compton sought advice and worked with people such as Ernest Lawrence, Harold Urey, and Enrico Fermi. In October 1914, scientists drawn together by Compton to a meeting in Schenectady, New York, concluded that the atomic bomb was feasible within 3.5 years. In December 1941, Compton became head of Plutonium Project, whose aim was to build a nuclear weapon based on the chemical element plutonium. This meant Compton was given responsibility for building the world's first nuclear reactor needed to produce plutonium. Plutonium had only been discovered a year earlier by Glenn Seaborg and his colleagues using 60-inch cyclotron in Berkeley, California. Compton decided to build a nuclear reactor at his own university in Chicago. A year later, on December 2nd, 1942, the world's first self-sustaining nuclear chain reaction took place under the direction of Enrico Fermi in a squash court under the stands of Stack Field, a University of Chicago football field. Compton was awarded the Medal of Merit for his wartime work. In 1916, while working for his PhD at Princeton, Compton married Betty Charity McCloskey, a former classmate from Worcester. They had two sons, Authur Jr., born in 1918, and John, born in 1928. John's middle name was Joseph. He was named for J.J. Thompson. Authur Allen grew up to join the government's Foreign Service, and John Joseph became a professor of philosophy at Vanderbilt University. In 1945, with his atomic weapons work completed, Compton returned to Washington University. In 1946, he became Washington's University Chancellor, retiring from his role in 1954, age 62. He continued working as a physics professor until 1961. Compton died age 69 on March 15, 1962 in Berkeley, California, following a cerebral hemorrhage. He was buried in Worcester Cemetery in his hometown of Worcester, Ohio.